Welcome. Is everybody ready to get started? Great, lots of exclamation points. Okay, let's get rolling. So we'll begin with some review of what we've covered so far in the first couple days of class. So here's a code block that has some examples of different types that we've talked about. So we've talked about just numeric values like 14 here, which, as we discussed, is treated the same way as something like 14.5 or non-integer value. If you want to get an integer, you have to put an L after it. So these are kind of very basic numeric types or integer types here. We also talked about lists, which are sort of ours. It's sort of a mashup of dictionaries and numbered lists from other languages, where you can name objects. You can pull objects together into a single grouping, and you can assign names to them. So for example, you might have a record which includes a name of Jessica and a role of special agent, all right? So you can put this kind of data together in a list. We talked about data frames, like there's a built-in data frame called Iris that you can just access by typing Iris. And we also talked about matrices. So these are what these things look like as they print out at the console in R. So we can tell that 14 is a numeric, 14L is an integer. All of this stuff is printing the list that we typed in here. And this $ here is reminding us that if we want to access a particular named entry in a list, we can use the $ in this way. And this is how a data frame prints. You can see that it has rows corresponding to observations and columns corresponding to variables or attributes. And then this is what a matrix looks like. And we remember we discussed that matrices in R are column-wise. So we had 1, 2, 3, 4, 5, 6, and we reshaped that into a 2-row, 3-column matrix. And it fills up the columns one at a time, rather than sort of, as you might expect, filling up the rows 1, 2, 3, 4, 5, 6 like this. Okay, so this is just a little reminder of some of the things that we talked about. I want to ask some questions to kind of jog our memories and get us going again for today. So first question is, what's the difference between a list and a vector in R? A list may contain all different types, and a vector must contain all of the same type. So nice job. Nice job with that one. So just a little bit of commentary on that. So lists are more flexible. You might think, well, let's do everything with lists. But there's some reasons why it's helpful to have vectors too. So for example, with vectors, you can take advantage of the consistency of the types to write faster code. So internally, the people who write the code that performs the various operations that will perform with vectors, they're able to exploit that knowledge of the types that are being stored to achieve much better performance than you would with an ordinary list type. And in Python, if you're familiar, this idea that lists are more flexible, so let's just use those, that's kind of where Python started, and it didn't have a vector type. But then people realized, for performance reasons, at some point you really do need vector types. And so they added that on, and that's the NumPy package in Python. So in R, we have both of those things, but they're built into the language. We don't have to have a separate package like NumPy to supply a vector type. Okay, and here's another question that we discussed the content of last time. What's the difference in R between a character and a factor column? So a column whose type is character and a column whose type is factor. Okay, nice job. So lots of people were on the ball with this one too. That's great. So a character column simply stores a character string for each entry. So every time you have a new row, you're going to store a value for that row and column, which is just a string, a sequence of letters or other characters. But a factor specifically stores a list of possible values, which are called the levels of the factor, in an auxiliary data structure. And then in the actual rows for each row, it only stores the level indices. So which of the possible values does this row correspond to? And that's more efficient. And it also communicates something about intent. You're not saying this is a value that could be any string in the world, and we'll just have to look to see what string it is. You're saying, no, this is a set number of possibilities. You might be talking about homes and then what kind of flooring they have. And it's going to be either wood or tile or carpet. a set list of values. And this is a way of communicating your intent that there's only a limited number of things that it can be. So as we talked about last time, one way to take a look at this and kind of see what's going on is to use the str function or structure function, which if we call it on the iris data frame, shows us that we have a factor with 3 levels here as the species column. So that's telling us there are only 3 possible values for the species, and all of the first, whatever number that is, in fact, it goes out to 50, are all setosa flowers. And then following that in this data frame, the next 50 are all versicolors. So you would see 2s in all of those positions. So it's a little bit more efficient to store these indices instead of storing the entire versicolor string, for example, for every one of those rows. So the next section is on vectors. So we've talked about vectors a little bit, both today and previously, as the thing that a data frame column is. So a data frame consists of several columns, and each of those columns is a vector. But let's dig into the idea of a vector a little bit more now. So these are the most basic objects available to store data. In fact, when you use a numeric value like 17 in R, that actually under the hood is a vector containing a single entry. So vectors are in some sense the sort of heart of R. They're the fundamental data type. And one sense in which they're the fundamental data type is that in many cases, more complex structures can be thought of as several different components, which are in themselves vectors. So for example, we saw a data frame where each column is a vector. So the first thing we should talk about is how to input a vector manually. So if you want to type in a vector, how do you do that in R? In other languages, you might have some square brackets or something like that. In R, we do this with the function C. And so we can call C with any number of arguments, and it's going to put them together for us into a vector. So we've seen this is how this particular environment outputs vectors with these central dots separating the entries. And so this looks good. It looks like we've successfully defined this 3-element vector. There's no reason it has to be numeric. We can just as well have character string vectors. So for example, we might want to put Italy, Canada, and Egypt into a vector. This is perfectly fine. These are all the same type. They're all character strings. And so we can do that. And now country is defined as this 3-element vector of characters. Incidentally, in R, like in Python, but not like in Julia, you can also use single quotes alternatively. And we will see a little bit of the back quote. So the back quote has a special role in R that we'll discuss. And that's a separate character from the ordinary single quote. They're on opposite ends of the keyboard, in fact. We'll talk about that a little bit more as it comes up. So if you forget the strings here, then you will get an error. So if you just do, Italy, Canada, Egypt directly as arguments to this function C, it will return an error because it's looking for Italy as a variable name, and we haven't defined that. So we haven't ever told R, when we say Italy, here's what we mean. Here's the object that we want to assign to that variable. And therefore, R is going to throw an error for us to tell us that we made a mistake. So one thing that seems like it would be a difference between vectors and lists is the ability to name entries. But in fact, in R, we can name entries in vectors too. So that's going to be something that's the same between the two. Both lists and vectors can handle sequential numbering starting from 1, or special names that we're typing in specifically for purposes of accessing these entries without having to keep up with the actual positions. So for example, if 380 corresponds to Italy, we might want to go ahead and name that here so that we don't have to remember later to get the first entry when we want the entry corresponding to Italy. So if we ask what kind of object this thing is, it's still the same, okay? It's not changing the fundamental character of this object. It's still a vector. You can still do the same stuff with it. It's a numeric vector because these entries, 380, 124, and 818, they're all numbers. But it does have names now, so we can we can ask what the names are for this vector using the names function. And it will tell us the names are Italy, Canada, and Egypt. So one thing I want to throw in here, this isn't in the book, but just a brief aside, because we will be using this. We've now talked about how to input vectors, and we actually skipped a lot of details that would have been nice to elaborate on, but we didn't have we hadn't yet developed the way of introducing or the way of manually inputting vectors, and so we can kind of go back and pick up some of those pieces now, and this is one of them. So if we want to define a data frame, we can use the data.frame function, and we just supply the columns as arguments with names given by whatever we want to name the columns. So this is a named argument with a named state, and the value is this 3-element vector. And this is the named argument with named region, and the value, rather than being a vector, it's a factor. So we started with this ordinary character string vector, and then we converted it to a factor using the factor function. And one nice thing about doing this in this way is that we can supply a levels argument to the factor function. And that allows us to say what order we want the levels to appear in, if in fact we have an opinion on the order in which they appear. So we might want to go sort of broadly speaking west to east, and we might want to choose this order for these two regions. All right, so if we run this code, then we get a data frame with exactly the data that we just put in it. So a couple of questions. Can you index a named vector by names? And the answer to that question is yes. We'll talk about that explicitly in a moment, but yes, you can. So the nice thing about using names is that you can then use those names to go into the vector and say, okay, give me the entry corresponding to whatever the name was, Italy, for example. So another useful function for creating vectors is the function that generates sequences, which looks like this. So it takes two main arguments. We'll see there are other arguments as well, but these are the two that really need to be there. And it just counts out the numbers from the first one to the second one, including both. So this is the way you count. If you've learned other programming languages, you learn that they sometimes count from 0, and that changes things a little bit about whether you want to include the right endpoint, all that stuff. Forget all that for R. It's exactly the way you learned to count when you were a little kid. You start with the first number, you end with the last number. Simple as that. So if we want to count up by a different value, we can supply that using a third argument, which I like to name, although you can also omit the word by here and just do 1, 10, 2. But this makes it really clear that we're counting by 2s here. So we'll start at 1 and we'll go up by 2s. And R provides the following shorthand if you do want to count by 1. So instead of having to type out the whole function seq, you can just use a colon between two numbers, and that means the same thing. So if we do 1 : 10, then it does exactly the same thing as sequence of 1, 10. One thing to be aware of, apropos of our discussion of the distinction between numeric and integer values, is that R does produce integer values for these sequence functions. And that's because they're usually used to index or count, and that's a natural integer role. So if we ask what the class of 1, 10 is, it will say integer. So the values being stored in that vector are integers. But of course, if we include values which are not integers, let's say we count by 0.5 going from 1 to 10, then of course it can't be integer anymore because it wouldn't be able to store some of the values that it has to store. Therefore, R will go ahead and make that a numeric vector. Okay, so I have another exercise for you. I'm weaving in more and more exercises as we go because we have more to draw on and more to start pulling together and more to remember. So it's going to be more important to have some exercises to kind of keep us on our toes. So here's a quick one. Write a line of R code, which produces the sequence 4, 8, 12, and so on up to 64. All right, so it looks like people feel pretty good about that. So it's sequence 4, 64 by equals 4. In some languages, you can put a second colon R does not have that. So if you want to count by something other than 1, you have to get away from the colon syntax and use the sequence function. We can use square brackets to access specific elements of a vector. So we've seen this before already with matrices, but if we want, for example, with the vector codes that we defined earlier, we can say codes bracket 2, and that will give us the second entry. And it even will print the name of that entry for us here in the output. We can also get more than one at once, not necessarily in sequence, by just supplying a vector as an index. So if you supply a vector of indices as an index to your vector, then what's going to happen is it's going to get those entries. So for example, here I'm saying 1 and 3, those are the ones that I want. Please give me the first and third entries from code. So I can run this, and it gives me the first entry, which is Italy, and the third entry, which is Egypt. And it skips the second one, which is Canada. And if you do want to access a block, a contiguous sequence of values from your vector, you can use the colon for that. So if we want the first 2, we can just do 1:2. We don't have to do C of 1, 2, although of course that would also work. And then in response to the question from earlier, if the entries have names, we can also use the names in the same way. So we can say, give us the codes entry, give us the Canada entry of codes, or we can say, give us both the Egypt and Italy entries. So this is going to be important for later. When we index a vector with a vector of indices, it just grabs them in order as we requested them. So give me the Egypt one, give me the Italy one. So we're going to use that in a more extensive and useful way in a moment. So here's a small indexing exercise. Write a line of R code which returns the populations of the first 10 states in alphabetical order. And by the way, this vector that you want to use here, it's the population column of the murders data set that we've been looking at. Okay, great. So people are taking some time with this one. So let's walk through it together, make sure we're all on the same page here. So I'm going to pop open my code cell. So as we just said, we have the murders data set. It looks like this. And if we want to grab the population column, remember that the population column is one of the entries in the list murders. So remember, data frame is a special case of a list. And the way that you access a particular entry of a list is with the $sign. So that's how we're going to grab that particular column out. And then we ask for the first 10. So we can just index that with 1:10. You could also use the sequence function here instead if you wanted to, or you could even type them all out, although I would not recommend that. And this is what we get. So the answer that we're going for here is murders $sign population bracket 1 to 10. And by the way, if you want to put this in a nice code block format, you might recall from earlier, the way you want to do that is put 3 backticks and then hit the space bar. And that will convert to this code block format. So I'll just send that so you can see what it looks like. Yeah, so sometimes something can happen with your network connection. So it looks like we have I'm still getting loading or nothing returned. So what you want to do here is probably just refresh the browser. That's like Command R, or click the little loop shaped icon with the arrow somewhere in your bar. Oh, right. Yeah. So it could be, yes. If you just do library DS labs data murders, that returns nothing. And so I should say as well, this business where you get the loading or nothing returned message, this is an artifact of how we're supplying the code cells in this environment. If you work at a real R prompt, it will distinguish those two things, and that's pretty helpful. But it's just when we send this off to the servers, if it doesn't return anything, it doesn't send anything back to us. So there's no way for the code cells in your browser to know the difference between those two things. So that's why I like to put done on the last line. That forces the return value to come back, and then you can actually know that that particular cell was run. Yeah, just another quick question here. How do you know it'll be in alphabetical order? It's sort of trusted information. So you can look at the data frame and check that. In this case, it was supplied as part of the exercise. If you wanted to order them, you would need to use another function, which we'll get to how to do that also today. But I said in alphabetical order because that's the order that they came in, and that way you don't have to resort anything, you just had to slice. Another sort of caveat here, especially if you're used to other languages, it's worth tipping you off in advance before you get bit by it. So coercion is an attempt by R to be flexible with data types. So you might try to do something that you're not supposed to do, like mix types in a vector, and what R will do is try to help you out. Okay, it doesn't say you made a mistake. It will try to guess what you mean and sort of roll with it. These are different philosophies in programming languages. You can try to be very strict to make the programmer do things correctly. That way the programmer knows as soon as they've made a mistake and they can make sure that everything's right on their end. Or you can try to be flexible and accommodate mistakes on the part of the programmer. That way you're throwing fewer bugs back at the programmer and they'll have a smoother experience, at least until they run into further downstream consequences of those mistakes. And in that case, that's where some of the frustration comes in with these conventions that are trying to be gracious. It doesn't always pan out so well. So this is one of them, but it does help a lot if you're aware of it. So that's why we're going to talk about it. So here's a simple example. Suppose I do C of 1 comma Canada comma 3, right, where Canada is a string. So this is mixing types in a vector, which you can't do. And yet we don't get even a warning. We don't get an error. It doesn't do anything. It's just happily assigns something to the name X. And we're going to have to see what, because it's definitely not mixing types. So let's check it out. Let's look at X and its class. And okay, the class is character, and the entries, this is not a 1, this is a string containing the character 1. And likewise here. So apparently what R did was look at the data, and it saw two numerics and a character. And it thought, you know what? I can represent all of these things as characters. I can't represent all these things as numerics. So let's do that. So we say that what R did is coerce the data into characters. So it's guessing that when you put 1, you maybe meant the string containing the number 1, and that way it can represent this vector with all the same type just fine. So you can, of course, achieve this effect exactly as we just did by mixing numbers and characters into the same vector. You can also, let's say you want to take the numbers 1 to 5 and make a character string out of it. So there are no characters there, so you can't just type one of them, type one of the strings as a literal string. But what you can do is call the as character function. That's going to convert X to a character string. So this does the same thing as before. It takes every number and sort of stringifies it, but it did so on command. You can convert it back with as numeric. So as we discussed briefly on a previous day, as dot and then any data type is going to be the function that converts other types to that type. And there's a question about whether we can forbid these kinds of automatic data type conversions. And as far as I know, you can't. So this is why it's important to tip people off about what to expect in this regard. It is much less dangerous if you know this sort of thing can happen. You can still make a mistake and not recognize that something is being coerced, but it will happen. For example, when you do statistics, that columns which contain strings are treated differently than columns that contain numbers, but yet still handled in some way. And so you might do a statistical analysis thinking that you're able to access that numeric data, and it's essentially treating all of those different numbers as different categories. So it can be quite bad, but if you know what to look out for, you can catch most of those mistakes pretty easily. So the as numeric function comes up more often than the other way, the as character function, because you will often encounter data sets in the wild, maybe things that are pre-packaged as R data frames, or something that is coming from some sort of comma separated values file where you're going to be reading that data in from some external source. and numbers might be stored as character strings, okay? And you want to treat them as numbers, so you want to use the asNumeric function to convert them before you proceed. So one important question here, which paves the way to a broader important discussion, is what happens when you try to coerce something that is clearly not coercible. So for example, suppose that we take a vector like 1 comma b comma 3, the character vector 1b3, and we try to convert it to numbers. So let's see what happens here. And of course, the rub is going to be that b is not a number, and we get a warning, so that's good. It's telling us NAs are introduced by coercion. So 1 and 3 converted fine, and then R threw in an NA for us for that second entry as a way of saying, I don't know what you're trying to do here, and I'm not going to try. There's no number I can meaningfully put here. The best thing for me to do is to say, this is missing. And these values, this special not available value, is important for lots of other reasons than failed coercion. You'll often have missing data. Someone conducts a survey and someone doesn't answer a question, or you have some patient data and one particular attribute was not measured in the clinic, and so it's left blank. There are lots and lots of reasons why data might be missing in the context of some data analysis that you're performing. And you need to sort of be aware of how various functions handle that. So we'll talk about that more extensively in a little bit, or perhaps next time. Okay, so here's a small investigation question. What does the sequence function do if the arguments are not compatible? So counting up from the first number by the specified jump size, you don't actually land right on the second number. So if you count by 2 starting from 1, what happens? So you can try it out and let me know what you think. Okay, so what happens is that it goes up to, but not past the stopping point. So if it hits the stopping point on the nose, it will stop there. If it goes beyond it, it only includes the values up until, it only includes the values before then. Okay, so let's move on to the next section, which is sorting. So we've got enough pieces in place here. We can actually circle back to our original question. All right, so we had a question earlier, how do you know the states are in alphabetical order? Fortunately, they already are, but you might want to choose some other order, and we're going to need to think about how to do that. So say we want to rank states from just the least to the most gun murders. That'd be the most basic thing you could do with this data set vis-a-vis analyzing safety. You can say, okay, what states have the least murders? What states have the most murders? Let's take a look. And the function for that, perhaps unsurprisingly, is sort. If you call the function sort on a column, it will sort the entries of that column. So for example, if we look at the total column, which tells us the total number of murders, then we get these numbers. So one state has only 2, that's amazing. And then it goes up to 1,257, which is much bigger than the next one up. So there's quite a spectrum here. But this is not really all that useful by itself, not least because we can't see which state is which. So when we extracted just the murders, just the total column, we lost information about the names of the states. And that's no good. We'd like to keep all the information around if we want. And the function that we want to accomplish that is the order function. So order is closely related to sort, but it's different in a way that makes it much more useful for this particular application. So it takes a vector as input and returns the vector of indices that sort that input vector. So it's worth looking at this and really breaking it down, but it's pretty easy for it to be confusing. Okay, so here's a vector of 5 numbers and we sort it. Everything there seems totally fine. This is what you're used to with the sorting operation. So let's look at how you would sort this list with the order function. What you would do is call the order function on the vector to obtain the collection of indices which sorts the vector, and then you index that with you index the vector with that new vector of indices. And that performs the same task. And let's break this down to see why it works. So if we actually look at the index object as well as the object X, and we can see what's going on. Okay, so this is the original vector X, and this is the sorting vector. So this is telling us if we want to put these in order, we need to grab the second entry first. In other words, we need to grab 4 first. We need to grab the third entry next. In other words, 15 comes next, and so on. The next in order is the first one. That's 31 here, etc. So at risk of belaboring this point somewhat, because I think this, maybe it seems quite clear here. It's easy to get confused by this, though, when you think about it later. So I want to give you a manipulative to practice this a little bit. So here are the first 5 states along with their populations. And I want you to drag them so that they're in increasing order of population. So smallest state to largest by population. And then use that information to say what's going to happen if we call the order function on the first 5 entries of the murders population column. All right, so this is maybe a pretty basic exercise. Lots and lots of folks are getting this right, so that's good. But I wanted to make it really visceral for you exactly what's happening. The row index from the original data frame is sort of coming with the whole row as you sort. And then the order just reads down, the order function effectively just reads down this row index column in the sorted list. So if we sort by this third column, what does the row index column look like? That's what the order function is doing for us. Okay, so we get 2, 4, 1, 3, 5, because that's the sequence that we see here after we sort these rows. Okay, how does this help us order the state by murders? In other words, what's good about the order function that the sort function doesn't accomplish for us? And the point is that the vectors that represent the different data frame columns, they're in the same order. So we can use this index, which appropriately sorts the rows to get the totals column in order. We can use that same one to sort other columns as well. So for example, okay, so just as a reminder, these things are in the same order: Alabama, Alaska, Arizona, AL, AK, AZ. These things line up. So if we use the vector returned by order to index, then, to index, let's say, the abbreviations column, then we're going to get the state names in order. So that's great. So Vermont was the one with an extremely small number, just 2, and here's some other ones that are quite low. And then towards the end, we have Florida, Texas, and California. So California was the one with 1257. That was the one with the most. Now, if we're only interested in the very largest one, we don't need to sort to find that. We can use the max function. So we can just do max of murders total, and that's going to give us this 1257 value that we saw earlier at the end of that list. We also might want the index for the same reason that we want the order function to exist. We want to be able to say, okay, well, the max is 1257, but where does it appear? Which row gives us the max? That way, we can use that row index to pull out other information from that row. The function for that is which.max. So if we call which.max on the murders total row, that gives us the index, and then we can say, okay, what state is right there? And sure enough, as we saw a minute ago, that state is California. Okay, so as a matter of interpretation, does this mean that California is the most dangerous state? And you might suspect already that the answer to that is no. You saw at the end of the list, we had Florida, Texas, and California. And if you know the United States well, you know those are 3 of the most populous states. So to a large extent, the total number of murders is a reflection of the overall population size. And safety for an individual in one of those states has much more to do with the murder rate than the total number of murders in that state. Here's a short question to practice a bit before we move on. So what's a simpler way to just write a line of code that's equivalent to order of murders total brackets 1. Okay, so to wrap this one up, sorting the row indices by total number of gun murders and taking the first element is the same as just asking which row does the minimum occur in. And that's the which.min function. I should also perhaps mention that last time it was requested that if you have if you have an anonymous peer response that you can then respond to, currently or previously the way it worked is that you had to respond to that person before other messages come in, or else your message would go back to the central classroom instead of to them. It's now possible if you type \peer and then hit the tab key, you'll get this same silhouette character. If you do that, then your message will go to the last anonymous peer response you received, rather than going to the central classroom, no matter what. So if you have any anonymous peer responses and you send a message that includes this busts and silhouette emoji, then it will go to that person. So that way, if I send another message and you think I really had something clever I wanted to say to that person, you can still respond to them. The window's not permanently closed. So that was a hat tip to Tom. He came up with that idea, and I think it was a good one. All right, here's another thing to watch out for with R. Speaking of potential gotchas. So in math, if you try to add vectors that aren't the same length, it doesn't make sense. If you want to add a vector, 11,5 to a vector 7,4,3, you go to add corresponding entries, and at some point you run out of entries for one of the vectors and you've got nothing to do with the other ones. It doesn't make sense, and it's not mathematically allowed. And in most languages, the vector type would throw an error if you try to add it to another vector with more or fewer entries in it, which is, I think, a very reasonable default behavior. R does not do that. R will do what's called recycling. So let's try to add 1, 2, 3 to 10, 20, 30, 40, 50, 60, 70. So you'll see what happens is that we get 11, 22, 33. That all makes sense. We just add corresponding entries here. But then we get 41. So where did it get that 1 from to add to 40? Well, it came back to the beginning of this vector. So this is called recycling. It goes through the shorter vector over and over again. And it will give a warning if they're not multiples of one another. So this had length 3, this had length 7, and it's like, hey, that might be a problem. But if one is multiple of the other, it won't give an error. It figures this person probably knows what they're doing here. And yet, you probably don't. Realistically, if you're trying to add vectors and they don't have the same length, you probably did something wrong. And it might be nice to get an error, but you don't. So you got to watch out for that. Okay, so here's another little exercise. I want you to create a data frame. So you're going to be creating a new data frame here. So each row should consist of a state name, as well as the population rank of that state. So for example, there should be a row that says Wyoming 1, because Wyoming is the smallest state in the United States by population, even if you include DC. And of course, every other state, California should be number 51. No, not necessarily in order. I just want the state name, and then the second entry in that row should be the rank. So I'll give you a chance to work that out or see how far you can get. So here's what I've got. We'll use the data.frame function like we introduced earlier. We'll have state as or rather murders state as the state column, and rank of murders population as the rank column. So here we have an example where the values are not named. So we supply the state column and the rank values, and this works. And it's actually totally reasonable, really, because the R is able to actually see what you typed in here. So this is a distinction, and I'll elaborate on this further later on, but this is the distinction between R and other languages. So we don't have what's called referential transparency in R. In other words, if I changed what I typed here, but in such a way that I got exactly the same vector out, it would actually change things in the result because I would get a different name right here for this column. So in Python, you cannot do this. If you type a variable name here, that's completely private, and this function cannot access that variable name at all. But in R, it can access the value, the vector associated with this name, and the name itself, and do things with both of them. So it puts the vector into this position, and it puts the name into this position. So anyway, what I'm going to do to avoid that issue is, and also just to give a cleaner name, is to supply names for the arguments here. So this gives us exactly what we want. We compute the rank using the population column, and we just grab the murders column, and this, grab the state column to use as our state column for our new data frame. And this is exactly what we want. We see that Florida is close to the end here. It has only Texas and California behind it. And Wyoming is number 1. Vermont is number 3. So all this checks out. If we look at this, this passes a sanity check. Here's a little question about ranking and sorting to help us. Actually, we're at the end of the hour. So I'm just gonna leave you with this question so you can think about it and answer it when you like. It's multiple choice, so it'll get an automatic reply based on your answer. I'm gonna avoid choosing one here. Let you think about that for a moment. And we'll pick up from here next time. So we'll continue with the R programming and basic stuff. I want to make sure to give this part of the course plenty of time because it's very important to have all of these fundamentals down solid, and then we can cherry pick a little bit more as we get into the data visualization stuff and try to do kind of some of the more fun things there and make sure there's, there's a real punchline within this course rather than sort of the basics kind of taking up all the space. But I do think it's really helpful to have this solid foundation. So I've decided to spend a little bit more time on this than was in the original schedule. And our next meeting will be next Monday. So enjoy the holiday break, and I look forward to seeing you next time.